Welcome to Thermodynamics, Lecture 2. At the end of the last lecture, we had ended with a statement of all the three basic laws of thermodynamics, stated, I confess, in a rather unorthodox manner. But we had also mentioned that in addition to these three laws, there's one more, and that law happens to be called the zeroth law of thermodynamics. Now, why does thermodynamics have such a thing as a zeroth law? And the answer to that lies in the recent, at least not too distant history of the subject. It was in the 1930s, by which time thermodynamics was really a very, very well established science, when Professor R.H. Fowler commenced writing his very famous and influential textbook on the subject. But while doing that, he realized that there is a serious lacuna in the logical structure of the subject. Thermodynamics, by its very nature, deals with something called temperature and heat. Fowler realized that temperature, which is a very fundamental thermodynamic quantity, was always taken to be something which existed for granted. But there was no statement in the standard treatments of the subject which actually talked about why temperature exists at all. So what Fowler did was coin a new law which would essentially state that this fundamental thermodynamic quantity, the temperature, exists. And this law should really have been the first law of thermodynamics. But by this time, the subject had a long and rich history, and the name first law had already been taken for quite some time then. So, since this actually should come before the first law, logically, Fowler called this law the zeroth law. And this zeroth law has to do with thermal equilibrium. Let me remind you, two systems are said to be in thermal equilibrium if they stay in equilibrium despite the wall between them being diathermal. Now, what the zeroth law actually says is, if a system A is in thermal equilibrium with a system B, and if at the same time system B is in thermal equilibrium with system C, then the systems A and C are in thermal equilibrium. Now, in order to illustrate this, I have drawn a diagram below. Here, I have denoted walls by two different notations. A wall with a solid coloring like this one indicates a diathermal wall, and this is an adiabatic wall. Remember, two systems can stay in equilibrium while separated by adiabatic wall, no matter what their individual states are. However, if they are separated by a diathermal wall, they would not be in equilibrium in general, but will come to an equilibrium which we call thermal equilibrium. Now, focus on the picture on the left here. Here we are indicating a situation where A and C are separated by an adiabatic wall, an empty rectangle here, whereas both A and C are in contact with the system B via a diathermal wall. And let's assume that each of the three systems have attained equilibrium. So under this situation, A and B, which are in equilibrium while being separated by a diathermal wall, are in thermal equilibrium with each other, and B also is in thermal equilibrium with C for the same reason. Note that at this stage, A and C are separated by an adiabatic wall, so we cannot directly say anything about whether they are in thermal equilibrium or not. What the zeroth law says is that if you now were to replace this adiabatic wall by a diathermal one, then it will be found that the states of A and C does not change with time. That is, A and C are already in thermal equilibrium with each other. So this was the statement of the zeroth law. Now, if this sounds like a familiar mathematical concept to you, congratulations. You have actually figured out that this relation between systems is in thermal equilibrium with is what mathematicians call a transitive relation. Now, just to jog your memory a bit of mathematics, relations are special things which occur between two elements of a set, and a very special kind of relation is what is called an equivalence relation. And this relation tilde will be called an equivalence relation if it has three properties. If it is reflexive, which is just a fancy way of saying A is related to A for all A. Similarly, symmetric is also valid for all A and B. It says that if A is related to B, then B must be related to A. And finally, we come to the transitive property of an equivalence relation, which simply says if A is related to B and B is related to C, this together will imply that A is related to C, again for all A, B, C. This symmetric statement was also for all A and B. Now, from the wording of the zeroth law, it should be obvious that it's really stating that in thermal equilibrium with is a transitive property. Now, what is important is this particular relation is obviously reflexive and symmetric. You do not need any law to tell you that. Every system by definition has to be in thermal equilibrium with itself if it is in equilibrium at all. So if you take all equilibrium states together of all possible systems on this set, this relationship is definitely reflexive, and since thermal equilibrium with is defined as a mutual property between both the systems, it's obvious that it is a symmetric relation. If A is in thermal equilibrium with B, then B has to be in thermal equilibrium with A. What zeroth law does is adds the non-trivial bit to this, the transitivity property. So what zeroth law ultimately ends up saying is that in thermal equilibrium with is an equivalence relation defined on the set of all equilibrium states of all possible systems. We will need a bit more maths for what is going to come next. An equivalence relation leads to the concept of what is called an equivalence class. The equivalence class of an element X of a set, written X within a square bracket, is simply the set of all elements Y of the set which are related to X through this equivalence relation. Now, one very important property of equivalence classes is that they are either disjoint or identical. If two equivalence classes, let's say the equivalence class of X and the equivalence class of another element, let's say Y, are not disjoint, that is, this is not the null set, then there must be some element Z which belongs to this intersection. That's what not being a null set means. There has to be an element there. But this will automatically tell you that Z has to be in relation with X and Z also has to be in relation with Y. Because the only way in which Z can belong to the intersection of this equivalence class and this one is that it must belong to both equivalence classes. But because of the transitive property of any equivalence relation, this immediately tells you that X and Y must be in the same equivalence class because they must be equivalent to each other. In other words, these two equivalence classes, if their intersection is not the null set, that is, if they are not disjoint, then they must be the same equivalence class. Not only that, equivalence relations are also reflexive, which means every element in the overall set belongs to at least one equivalence class, the equivalence class of itself. X must belong to this particular set. Now we state both of these statements together by saying that equivalence classes partitions the underlying set. It breaks up the underlying set, whatever it is, into subsets, one equivalence class in its own subset, and these equivalence classes are all non-overlapping. So they are either disjoint or identical, and every element is somewhere here. So the union of all these equivalence classes gives you the entire set. This is what is technically called a partition, a bunch of disjoint subsets of a set whose union forms the entire set. So given any equivalence relation on any set, the equivalence classes corresponding to that relation partitions the set. And this concept is going to be very, very important for us simply because in thermal equilibrium with is an equivalence relation, and so it will also define its own equivalence classes, which will partition the collection of all states of all systems into disjoint pieces. Now, exactly what will these disjoint pieces consist of? They will consist of states of systems which are all in mutual thermal equilibrium with each other. Note that in this case we are not necessarily saying that you have brought them into contact through a diathermal wall and the states have not changed. We are simply saying that if they were brought in contact via a diathermal wall, their states would not change. In all this, we are already assuming that all the walls we are talking about are rigid and impermeable. So, the only way equilibrium could be disturbed was via a non-mechanical or non-chemical way, something which is unique to thermodynamics. Now, these collections of all systems that are in thermal equilibrium with each other, this defines the partitioning of all states into these disjoint pieces which we call isotherms. So isotherms are really collections of all states of all systems which would be in mutual equilibrium with each other. Now, one important thing about an equivalence relation is that an equivalence relation is so useful for us basically because it's really equality in disguise. Note that is equal to is reflexive, symmetric, and transitive. A is equal to A equals B implies B equals A, and A is equal to B along with B is equal to C actually implies A is equal to C. Indeed, an equivalence relation is a generalization of the concept of an equality. And so whenever you have an equivalence relation, there is an underlying equality lying somewhere. In fact, this equality is rather easy to figure out. Each of the isotherms in this case can be given a unique label. Now this label could be tunes which are unique to each partition, could be something else altogether, could be a picture which you affix one to each isotherm. But the most common thing that we use are numbers because they are easy to deal with. So we will assume in the rest of this lecture and the rest of the entire course that this labeling is being done by a bunch of numbers, a different number for each isotherm. This label is what we call an empirical temperature. So temperature is simply a label which tells you that states of systems which share the same label are in thermal equilibrium with each other, and states which have different labels belong to different isotherms, so they are not in thermal equilibrium with each other. Now a question that may have come to your minds is exactly what does this particular adjective, empirical, mean here? Note that as we have said, at this point the temperature is only a label that tells you whether a system will be in thermal equilibrium with another system or not. And this label can even be changed as long as you maintain the different labels for different isotherms rule. such a change will have no physical effect whatsoever. In particular, if we are using a numerical value, theta, for the temperature, then a monotonic function f of theta is equally good as the temperature. So at this point at least, there is nothing that sets one temperature as superior to, or in some ways more useful than another temperature. So these are temperatures which have been assigned on an empirical basis, just on the basis of an experimental fact of thermal equilibrium or non-thermal equilibrium. And why exactly does this function f of theta have to be monotonic? To illustrate that, let us just show you what would happen if we were to use an f of theta which is not monotonic. A function f of theta whose graph, say, is the blue curve here. Now in this case, notice that two different values of theta, namely theta 1 and theta 2, both give you exactly the same value of f of theta. So f of theta 1 is equal to f of theta 2. Now in this case, what would happen is that two distinct isotherms, which were labeled by different numbers theta 1 and theta 2, in your original temperature that you were using, now ends up having the same label f of theta. So systems which were not in thermal equilibrium before, systems belonging to isotherms labeled by theta 1 and theta 2 respectively, would seem to be in thermal equilibrium according to this new labeling. Of course, if they are not in thermal equilibrium, they cannot be in thermal equilibrium just because you have changed the label. All that would mean is such a change of label is something you should not do. Changes of label are fine as long as each value of theta corresponds to one and only one value of f of theta. A typical situation would be one in which f of theta is an increasing function. Could be a straight line, could be a curved line, but an increasing function. Indeed, it could even be a decreasing function, and frankly, nothing would go wrong as far as labeling of isotherms is concerned if the new f of theta was a decreasing function of the old theta. But there is something else that we actually ascribe to temperature, something we have learned from childhood, that heat flows from a higher temperature to a lower temperature. If you want to keep on maintaining that while changing your temperature label, you would actually have to use monotonically increasing functions and not decreasing functions. Having said that, this still begs the question, why is it that heat flows from a higher temperature to a lower temperature? The answer to that, funnily enough, is not in the original version of the zeroth law. In fact, it cannot be in the original version of the zeroth law because logically at this stage, we have not even defined what heat is. That is going to come later through what is called the first law of thermodynamics. However, what we will do is sort of make a logical leap here, assume that everybody here knows what heat really is and knows that it is heat flow which occurs between two objects at different temperatures which disturbs their equilibrium when they are connected through a diathermal wall, and try to understand how we could modify the zeroth law to ensure that the statement heat flows from higher to lower temperatures has a consistent meaning. At a first glance, this may seem like a trivial matter. After all, if two bodies are not in thermal equilibrium, then the states will change and heat will flow from one body to another. Of course, as I have said before, we are making a jump in the logical sequence here in order to speak about this. Heat is something we are going to logically introduce in a proper logical sequence later on. But for the time being, we are assuming that everybody knows what heat is and proceeding from there. Now, heat of course flows from the hotter body to the colder one. But there is nothing profound in this statement. All we are saying is the body from which heat flows out is what we are going to call hotter, and the other one is going to be called colder. So, this is just nomenclature, or is it? Actually, one more important thing is sort of implicit in this. We are actually assigning transitiveness to heat flow. We don't just say hotter and colder. We say that heat flows from higher temperature to lower temperature. If, of course, the two bodies are coupled or connected by a diathermal wall. Now, what transitiveness means here is the following. If heat flows from system A to system B when they are in contact with a diathermal wall, and from B to C when that pair is in contact with a diathermal wall, then if A and C were connected through a diathermal wall, heat would flow from A to C and not from C to A. This is transitiveness. Now, the point is, the moment you say something like heat flows from higher temperature to lower temperature, you are actually taking it for granted that heat flow has to be transitive. This A to B, B to C, implying A to C heat flow has to occur and not the other way around. If heat could flow in a circular fashion as shown in this picture, from A to B, then from B to C, and from C to A, this assignment of higher temperature to hotter bodies and lower temperature to colder bodies would simply not work. Because since heat is flowing from A to B, you would have to assign a higher temperature to A than to B. But then, since heat is flowing from B to C, you would have to assign a higher temperature of B than to C. But a standard property of real numbers, which we are using for temperatures here, is that if A is greater than B, which in turn is greater than C, then A is greater than C. This is, of course, the transitive property, which, in addition to equivalence relations, order relations also have. On the other hand, if heat then flowed from C to A, we would be in big trouble because now C would have to have a higher temperature than A, which would be inconsistent with the transitivity of the greater than or less than order relations that we are used to. Now, nature does not allow this kind of circular flow of heat, which saves us in our quest to assign higher temperatures to hotter bodies. But is this really a consequence of the zeroth law? Of course not, because the zeroth law talks only about thermal equilibrium and not about what happens when two bodies are not in thermal equilibrium. In order to establish this as an experimental statement or experimentally obtained statement within the structure of thermodynamics, what we need is what is called the strong form of the zeroth law. And that is the following. This is the zeroth law in a strong form. Actually, strictly speaking, it's a converse to the zeroth law, but who's nitpicking here? If three bodies are in thermal equilibrium, then any two of them would be in thermal equilibrium. Now let's see why this version of the zeroth law tells you that circular flow of heat from A to B, B to C, and then from C to C back to A simply cannot exist. Now, if you did have a situation like this, that heat could flow from A to B, B to C, and back from C to A, then we could actually adjust the rates at which heats are flowing simply by maybe changing the thickness of the barriers in between, so that this situation is created. The amount of heat flowing out of A into B is exactly equal to the amount of heat flowing out of B into C, and that is exactly equal to the amount of heat flowing out of C into A. All you would have to do is adjust the walls between A to B, B to C, and C to A to appropriate thicknesses, and you can essentially end up with this condition. But now let us look at what is going to happen to any of these individual systems. Whatever heat is coming into A from C is going out from A into B, so A is neither losing nor gaining any heat in the process. The same for B, the same for C. As a result, each of the three systems A, B, and C can remain in equilibrium without any of their coordinates changing, despite this circular flow of heat. could have is a situation where the three bodies A, B and C are in contact through diathermal walls, but their states are not changing with time. This is exactly what we mean by thermal equilibrium. So in this situation, the three objects or three systems A, B and C are in thermal equilibrium. However, note that here the presence of all three bodies is necessary in order to maintain thermal equilibrium. If we were to remove, say, C, then heat will flow out from A to B, and B, of course, cannot lose that heat to C any longer because C is no longer there. And the heat lost by A cannot be regained by it flowing in from C because we have removed C from the equation. So notice that in this case, although A, B and C are in thermal equilibrium, any pair of them, if you remove one of them, whatever pair is left, will not be in thermal equilibrium, thus contradicting the strong form of the zeroth law. So this is why if the zeroth law is correct, then you cannot have a circular flow of heat. And that means if heat flows from A to B and then from B to C, it has to flow from A to C. And so an assignment of temperature such that A has the highest, B has lower than that, and C has an even lower temperature will be perfectly consistent. If you were to connect C and A through a diathermal wall, A would have a higher temperature than C, and heat will flow from A to C, not the other way around. Now, if you think about it a bit, it should also be quite clear to you that this transitivity property which allows us to assign a higher temperature to a hotter body, the body which loses heat, is actually also consistent with us assigning a lower temperature to a hotter body. If you did that consistently, again everything will be alright because A is less than B and B is less than C would then imply A is less than C, and therefore heat would again flow from A to C if this were your convention that heat flows from lower temperatures to higher temperatures. So whether you say heat flows from higher temperatures to lower temperatures is your prerogative. Well, it's really not your prerogative because, well, hundreds of years of tradition has established a way of talking about temperatures. But we could have used a temperature scale in which heat actually flowed the other way. Indeed, such scales had been used in the past. And not only that, when you talk of the microscopic picture underlying thermodynamics, statistical mechanics, the quantity which plays the role of temperature is something which we denote by beta, and it's actually 1 over the Boltzmann constant times the temperature in what is called the absolute scale. We often talk of beta as the inverse temperature, but strictly speaking, it is just as good a temperature as any. It's just that heat flows from systems with a lower beta to one with a higher beta. And because of tradition, we don't really call beta a temperature, but rather the inverse temperature. Now, with all this talk about temperature comes a very important question. How do we measure temperature? After all, physics and especially thermodynamics is an empirical science. Everything that you talk about should be measurable. What you measure temperature with are things called thermometers. These are pretty familiar objects from daily life. But in the logical structure of thermodynamics, thermometers play a very important role. We are going to talk about them in the next lecture.